Okay. We're just about, yeah, it's 11. So I kind of anticipated that today we would have low attendance given the weather. And then I had another student who, long story short, I need to record today's class, right? Because this is actually an important class. And what we're going to do is hard to explain easily. So I'm recording today's lecture. I'll post that later, and I'll send out the link for everyone. All right. We have a question about the homework. I will address it in a moment. I wanted everyone to take a look at this quote real quick. Wanted to see if anybody recognized this quote and maybe knows what movie it's from. No? Doesn't look familiar? I'll give you a hint. The main stars of this movie are Brad Pitt and Ed Norton Jr. No? Yeah, I think no. What? Fight Club. Yep, this is from Fight Club. If you've never seen Fight Club, don't worry about it. You don't need to have seen it, all right? This is really tight in here today. Just pick another seat. I think other people aren't going to be here. Just pick a seat where you'll be comfortable, okay? Yeah, if you've never seen Fight Club, don't worry about it. But this this quote, first time I ever heard it in the movie, I was like, oh, yeah, that's a mathematical concept, right? So it says here that if you think about a graph of something where the x-axis is time and the y-axis is the probability that a person is alive. Okay, so think about it this way. And we're talking about just general like humans, right? You're born, right? So you're alive. We're not going to get into a debate about when life begins and all that shit, right? We're just going to say you're alive. As time goes on, you get through the infant stage of your life, it can be a little bumpy there. You can have some sicknesses when you're young. Once you get past a few months, a few years, probability that you're alive is good. But what happens as time goes on, right? What do you think the probability is that a human being is going to make it to 20 years old? Let's say this is measured in years. Years. Good probability. An American living in first world country is going to make it to 20 years old. Pretty good probability. Pretty good chance. Yeah. So if we say that 1 is 100% probability, like 1 means 100%, then the probability that a human's going to make it to 20, an American, let's say, is pretty good, right? Not guaranteed, but pretty good. But what happens as time goes on? What's the probability you're going to make it to 75? Well, not that good, right? It's going to be lower than this. How about to 100? Good or bad probability? It's going to continue to drop, isn't it? My wife's grandfather passed away last year. He was 104. So I know people make it past 100, right? So the probability you're going to make to 100 is pretty low, but some people do, right? How about to 110? What do you think? Pretty small? Could it happen? Yeah? So 110? Really small? How about 200? Probability you make it to 200. What do you think? You think are you comfortable saying 0? Like there's no chance you make it to 200. Are y'all comfortable with saying no chance? Yeah? Yes? Come on. Yes or no? Yes? No chance make it to 200. Okay. So how about 199? No chance? 198? When is it not 0 then? Because at 110, there's a chance. Right? Hey, it's real tight in here today. Just pick another seat because I don't know what happened in here. Right? It seems like really, I think they moved. I'm not sure what happened. Who cares? All right. So if you're going to tell me, just pick any seats, or they rearrange the room. It's hard to find a place right now. All right, look. If you're going to tell me that is 0, then, and you're going to tell me that 110 is not 0. You've got to tell me between 110 and 200 when it actually reaches 0. It's hard, right? I mean, like when, what is it, 150? Is that still 0 to 150? Yeah, y'all still 0? 120? Still 0 or no? You see the problem? There's a problem here. You don't want to sit here and say that there's no chance someone lives to be 200. Mathematically, we can't do it that way because there is some chance that someone will live to be 200. But it's a very small chance, right? It's very, very small. Okay, we've got a problem here with seats, so I don't know what's going on in this room. Why don't you roll around the edge? Yeah, like that. Is that comfortable, okay? All right. So, do you understand there's a problem here? We can't say 0 because then when exactly does it hit 0? That's what this is saying. On a long enough timeline, the survival rate for everything drops to 0. Doesn't ever get there, okay? So I really want you to think about this more. This graph looks like this so far. Connects, gets smaller and smaller and smaller, right? And here's where we are. We're not quite sure what to do now. What do you think is more likely? Okay, what do you think is more likely? That you'll live to be 110 or that you'll win the lottery in your life? What do you think is more likely? You live to be 110 or you win the lottery? What do you think is more likely to happen? You think you're more likely to live to 110? Yeah? You think it's lottery? Okay, so what do you think is more likely? You live to be 110 or you win the lottery twice in your life? What's more likely? You think you're more likely to live to 110 than to win the lottery twice? Could you win the lottery twice? Could you? Yes. I mean, if you played it, you could, right? But the odds are very, very small. Are they 0? No. So when I say a person lives to be 200, I don't want you to say the probability is nothing. I want you to think of it as being this infinitesimally small number. And when I say infinitesimally small, I mean this. Think about like winning the lottery. Like, what are the odds of me winning the lottery every day I'm going to play the lottery after school today. I'm going to go buy a ticket, right? What's the probability that I win every day for the next 365 days? 365 days in a row, I win the lottery. Could it happen? What's the chances? Like, infinitesimally small, right? So, when we talk about drops to 0, we're talking about something that's getting smaller and smaller and smaller and smaller and smaller, but never actually ever getting to 0. All right? Never getting there. Another thing you could think of that doesn't have to do with like living things, just your phone, right? Think about your phone. When you buy your phone, the battery is really good, right? Lasts all day, into the next day. Okay, 6 months later, does it last that long? No. What happens over time? Starts to drop down, right? If this is hours or whatever, it lasts, right? And then this is the days you've had your phone, something like that. Then as you go on, it drops off, right? So do you think that in 10 years, if you turn on your battery or turn on your phone, it's going to work if you still had it, right? Would it still work? Maybe, right? In 20 years, maybe, but it's dropping down. You can't say 0 though. There's no you can't say at exactly 10 years, it won't work, right? There's always that chance it'll continue to work. So what we need are functions that represent real world behavior like this. These things happen in the real world. So we need some functions that behave this way. See how it's dropping down and getting closer, never touching? We need a function that does that. And out of all the functions we've studied, none of them do that, right? What do we have? Lines? Because I'm recording, I have to stay between that dash and that dash. So far we have lines, right? Lines, they don't flatten out like this, right? They don't do this. We have parabolas that do that, or they go the other way. They don't do that, right? And then we've got these polynomials that we've been studying that do this, or they can do that, or that, or that, or that, right? All this. They don't do this as well. So we need a new type of function that will behave this way. And that's what brings us to today's topic, our newest function called rational functions. The worst ones, these are the worst. These are the hardest to graph, all right? So we are going to cover today rational functions so that we can get something that behaves this way. Gets closer and closer to something without actually getting there. So today is about rational functions. But before I get into today's stuff, I was asked about the homework. So was it the one where I drew the picture and you gave me the function? Is that what it is? I'm going to have to look at the picture. Do you have it? I'll come over there. Maybe, if I can find my way. That's good. So it hits at -3, -2, 0. So -3, -2, 0, 2 and 4. Keep it there, hold on. And it goes, crosses through, bounces off 0. Bounces and bounces, like that. Okay, that's our graph. Thank you. I'm going to go do it over here. So what is your question? Can you have different answers? Is that?
Yeah, no, I got to the answer, but then I was wondering if it was like not reduce it, but like kind of combine things.
Can I see what you got? Can I put it up here?
Sure.
What the hell? No, I'm kidding with you. So this one right here?
And then like the one in the bubble on the side, that's what like I thought maybe.
Oh, like could you put it together? Okay, got you. All right, so this, I think you put a negative in there. Okay, so let me put it up here. Let me do this first. So when I look at that, I know that I need x plus 3 here, right? That takes care of the first x-intercept. I need x plus 2. I need x. I need x minus 2. I need x minus 4. Who has questions on that? No? No? What next? The exponents, right? You need to know the powers on these. So at -3, which comes from here, I cross through, right? Which means I need a odd number here, so I can just leave it as a 1. Here I need to cross through as well, right? So just leave it as 1. Then at 0 I need to bounce. So squared, okay? At 2 I need to bounce, so squared again. And then at 4 I need to bounce to squared again. All right, that takes care of all the x-intercepts and the bouncing and the crossing. What's the last thing I have to consider? Are you all okay? Yes, I need to figure out the left and right hand behavior. So right now, as it sits, this acts like an x to the first power. This acts like an x to the first power. This acts like an x squared. This one acts like an x squared. And this one acts like an x squared. So all I'm doing here is taking the 1 in front of x, squaring it. The 1 in front of x, squaring it. The 1 in front of x, squaring it. The 1 in front of x to the first power. The 1 in front of x to the first power. So I get that, which is 1 in front of x to the 8th power, right? But that would do this on both sides, right? I don't want that. I want this, right? From the picture, I want both sides down. So that means I need to make, the easiest way is just put a negative in front of the whole thing, just like that. Now, I think you put the negative inside, right?
No, I was actually talking about number 6, but it still works for number 5 as well.
Oh, okay.
Like what I think. Like, yeah. I see what you do. Like, do you know what I mean?
I don't know. I don't know.
Because you have like an x plus 2 and an x minus 2.
Could I put those together? Yes, but if I had x plus 2, if this one's squared, then I would not put those two together. So don't try and multiply them back together. Just leave them all torn apart.
Okay.
Yeah, leave them the way they are.
So you could do like the difference of squares?
You could put them back together. You could, but you don't need to.
Okay.
You don't. I wouldn't. Just leave it. Yeah.
That's
So
Yeah.
last time you said that we couldn't put like the -1 in front of something that's squared, but if you put it in front of the x that's by itself, so you take away the parentheses, put that away.
Well, you can't put it in. You couldn't put the negative here inside of this because it's squared, or the negative here, or the negative here. You could only have made this one a negative or this one a negative. That's it. But when you do that, then you have to change these to negative. So that's why I told you last time, just put the negative on the outside. Just put it on the outside. You're safe that way. Okay. Does that kind of help? All right. So are y'all ready to turn this in, or do y'all want to turn it in? You don't want to turn it in? How many of you have it done? I'm not going to be upset. Okay. So look, if you have it done, turn it in. All right? Because I asked you to have it done. If you don't have it, bring it to me next time. You won't get full credit, but you'll get something. All right? All right. So I'll collect those. And we're going to move on. Anybody else? Anybody else? You had a question? You want to ask me after class?
No,
Or-
so I wasn't here last class,
Oh.
so I watched the video on kind of how to do it.
Yeah.
So I got that, and I don't know if that's wrong.
I can look at it after. Yeah. Why don't I'll put yours on top, and afterwards we can just kind of look at it. What else
I
here?
turned the last one as well.
You can turn the last one as well, but same deal. You know, it's late, but it's better than nothing. All right. All right.
I have the last one as well.
Okay. So let's see. This is
That's the
the one for now, and this is the last one. All right. Thank you. All right. Down to business. So what is a rational function? What did we just finish studying? What are the types of functions we just finished? Polynomial functions, right? You all know what a polynomial looks like, right? Okay. Here's what a rational function looks like. It's a function, and all it is, it seems real simple that it is a very simple definition, but it turns out to be a nightmare for us. All it is a fraction, okay, where the numerator is a polynomial, the thing we just studied, and the denominator is also a polynomial, and they're different polynomials. So everything we've been studying, take one of those and divide it by another one of those, and that's what a rational function is. So did you say disgusting? That's a good description. I like that. All right, so I'm going to start with a very basic example, all right? And when we start with it, what we're going to do is we're going to just kind of look at it like old school style. Thank you. When I say old school, remember when you first started graphing, you did like t-tables to like figure out what happens if I plug a number in. We're going to do that, and we're going to get like the basic behavior of one of these. And then once we get the basic behavior, then I'm going to give you the steps. You know how we've had steps for all these things? I'm going to give you steps. And the steps are going to suck. I'm just warning you, all right? So here's your first example. Let's do something like this. Let's take, how bad do we want this to be to start? Let's do this. X over x minus 2. That is your first example that I'm giving you of a rational function. Now, the top is a polynomial because it's x to a power, right? And that's what polynomials were. Polynomials were with x's to different powers. And that's a very simple polynomial because it's just x to the first power. And the bottom is x to the first power minus 2. So it's a very simple polynomial on the bottom as well. And what I'd like to do is figure out what this thing looks like. All right, so let's do this. Y'all have a calculator? Everyone got, or a few of you have calculators? We're going to need some help here. I'm going to do a graph over here. And over here, I'm going to do a t-table. Now, just keep in mind, this is not the way we're going to do these. Okay, this is just so we can get an idea of what this looks like. So here's x and here's the function. All right, so let's start with something simple. Let's plug 0 in. So what would happen if you plug in 0? On the top you get 0, right? And then what's 0 minus 2? Negative 2. So 0 over negative 2, that's 0, right? So if I plug in 0, it spits out 0. So I have this point on my graph, right? That's my point. 0 goes in and 0 comes out. Let's try 1. What happens when you plug in 1? What do you get on top? 1. On the bottom? 1 take away 2 is negative 1, right? So you have negative 1. So if I plug in 1, it spits out negative 1, so I'm down here, right? All right, let's plug in 2. What happens when you plug in 2? On top you get what? 2. On the bottom you get, 0. Division by 0 is undefined, right? So there's something wrong with this graph right here. We have a problem. Every graph we've done up to this point, we've never had a problem, right? We've always been able to plug numbers in to the parabolas, to the lines, to the polynomials. We've never run into an issue like this before until today. So at 2, we have an issue, right? So here's what I'm going to do. At 2, because I have an issue here, I'm drawing a vertical dotted line like this. And that just reminds me that at 2, the graph is having an issue, all right? Okay, 2 didn't work. This is where I'm going to need your calculator. Let's try something that would have been close to 2, but not actually 2. So how about 1.5? So if you plug in 1.5, you get 1.5 on top, and then 1.5 minus 2. Don't understand what I'm doing? On top I have 1.5. On the bottom I have 1.5 minus 2 is negative 0.5. And I believe if you do that, you can get negative 3. Yeah, negative 3. So at 1.5, right here at 1.5, here's 1, here's 1.5. I'm down here at negative 3, negative 1, negative 2. So that's right here. Do you see it, the point? So it looks like my graph right now is doing this, right? Let's try a number that's closer to 2. 1.5 was pretty close, right? Let's go closer. How about 1.9? Let's try 1.9 in there. So I'm going to come back up here because, again, I'm on camera, so I want to make sure I get this. Let me try 1.9. You get on your calculator, we're going to do 1.9 plugged in here. 1.9 in here is going to be 1.9 over 1.9 minus 2. That's 1.9 over negative 0.1. What are you getting? Negative 19. Where's that? Way down there, right? Way down there. Actually, it's so far down there I can't even show it to you on this graph, right? So if I go to 1.9, I'm way down there. What do you think would happen if I went to 1.99? 1.99. Be even further down. What about if I went to 1.999? Further down. 1.99999. Further down. And I could continue that for the rest of my life and never get to 2. So what we have in this graph is something we've never seen before in a graph, where we have this like vertical, it's almost like I act like this is like a wall, like a barrier. And what's happening is the graph is like going towards that barrier. It's like, shit, I can't hit the barrier. So it turns away and it starts taking off down here like this and just goes forever down, getting closer and closer to the wall, but never actually hitting the wall. Make sense? Sure? This is a strange shape, right? We haven't seen that in a function before. Let's go to the other side. Let's plug in 3. Let's see what happens when we plug in 3. Had we plugged in 3 yet? No, right? Plug 3 in, you get 3 over 3 minus 1. This is 3 over 2, which is 1.5. Yeah? So at 3, we don't have a problem. We're up here at 1.5. put that up a little bit more. Yeah? No issues there? How about if we got closer to 2 from this side? Like, how about we plug in 2.5? I want to see what's happening here. 2.5. Plug it in, 2.5 over 2.5 minus 2 is 2.5 over 0.5. What do you get there? 5? You get 5? Yes.
So 3 is supposed to be 3 minus 2, right?
3. Oh, what? Yeah, sorry. This is, yeah, thank you for pointing that out. I think I had done it in my head and I put 2 there. This is 3 minus 1, or 3 minus 2 is my mistake. 1, that's a 3. Thank you for pointing that out. That's incorrect. Yes? So that number's actually up a little bit higher, isn't it? Like right up here somewhere? Y'all follow that? So if we did 2.5, which is right here, the number comes out to be this divided by this. I think you get 5 here, right? So what does it look like? What does it look like is happening here? As I'm getting closer to 2, where does it look like the point's going? The points are going up, right? It's the same thing that was happening on the other side, except instead of going down like this, it's actually turning up like this. And we could keep putting more points closer and closer. I'll do one more. Watch, if you don't believe this, how about 2.01? Try that number in there. That's right on the other side of 2 there. If we do that, you get 2.01 over 2.01 minus 2. It's 2.01 over 0.01, something like that. Is that 200 or something? 201? It's huge, right? Huge number. So if I'm to the right of 2, I'm way up there. If I'm to the left of 2, I'm way down there. See it? Strange. All right. Well, let's see what happens when we keep going this way. Let's see what the graph does if I keep going to the right. So let's plug in a bigger number. Can we plug in 10? Let's plug 10 in and see what we get. So if I plug in 10, I'm going to get 10 over 10 minus 2. That's 10 over 8, which is like 1.25. 1.25. So if I'm at 10 now, I'm going to go off my camera here. So I'm going to put 10 right here. I'm at 1.25. What happens if I go to 100? What's going to happen? 100 over 100 minus 2, that's 100 over 98. What's that on your calculator? 100 divided by 98. Should be 1.02. It's really close to 1, isn't it? What if we did it? This is the last one I'm doing. What if we went to, let's go to 10,000. That's way out there, right? That'd be 10,000 over 10,000 minus 2. This is 10,000 over 9,998. That should be like 1.00, I think 0, another 0, 2 or something like that. Really close to what? 1. It appears that as I go to the right, what's happening is that my graph is getting closer and closer to 1 as I go out this way, right? So imagine that we have, I'm going to use a different color. Imagine that we have this line. Let's say this is 1 right here. Imagine we have this line out here that's 1 unit off the ground, like this. What's happening is my graph is getting closer and closer to 1, but never getting there. Okay, so this is like what we started class with. Survival rate for everything drops to 0 without, right? This is the same thing, but not 0. Here it's up at 1. Got it? Now, if we go the other way, we haven't even talked about negative numbers, have we? We're not going to continue. But if we did negative numbers, here's what we would get. Our graph would do this. It would also flatten out over here. Remember this was 1? It would be 1 over here as well. It would get closer and closer to 1, but it would come up from the bottom instead of coming down from the top. That is the graph of this function, all right? That's what it looks like. So I want to point out some things. We're going to have some new terminology. Anywhere the graph hits the x-axis is an x-intercept. In this particular graph, I have one x-intercept, don't I? That's where it hit the x-axis. This place where you have this thing going where the graph goes down on one side and up on the other side, this line right here, this dotted line has a name. It's called the vertical, this is a weird word. Let me write it down first. The vertical asymptote. It's a weird word. Asymptote. Asymptote. The P is silent. Asymptote. Vertical because it's a vertical dotted line, right? And then we have this other characteristic of a rational function, which is this horizontal dotted line. You see it here and here at the edges? That is called our horizontal asymptote. Now here's the thing that sucks, all right? Even though these are characteristics of a rational function, not every rational function has x-intercepts. Not every rational function has vertical asymptotes. Not every rational function has horizontal asymptotes. And sometimes we have more than one of these, and sometimes we have more than one of these. So every rational function is just different. It's like a different animal, every single one of them. But these are the main characteristics of a rational function. They have maybe x-intercepts, maybe vertical asymptotes, maybe horizontal asymptote. So when we go to graph these things, what we're going to do is the way we're going to go about this is we're going to say, okay, first thing we're going to do is we're going to figure out if we can find out where the x-intercepts are. The next thing we're going to do is figure out if we can find out where the verticals are. And then the next thing we're going to do is find out where the horizontals are. And then once we can kind of get an idea of what those are, where they are and where they're happening, we'll try and draw the picture. So it's a pain in the ass, okay? It's a pain in the ass. Let me see if you can tell me how the x-intercept, that's at 0, right? That's where the x-intercept is? How does that correspond to that function? Like, what, now, knowing this now, what is it here that tells you that we have an x-intercept at 0? What is it here? Isn't it just when the top is 0? Like if I ask you right now, what makes the numerator 0? What would you tell me? 0, right? Like what do you plug in here to make the top 0? You tell me 0, right? Well, that's where the x-intercept is. If I say over here, what makes the denominator 0? What would you tell me? 2. And what's that over here? The vertical, right? The vertical is happening at 2. That's the connection we're going to have. Anywhere where the top is 0 here is where we have an x-intercept. Anywhere